All right, so we've looked at how to model motion based on constant forces, variable forces, any kind of forces that you want. But all of the coding we've been doing so far has been in one direction, just the x. What I'd like to do now is add in all the same stuff for y, because you can have an object moving in 2 dimensions. We move in 2, 3 dimensions all the time. So let's do this. Let's clean up our notation here. Let's make this the force in the x direction. Let's make this the acceleration in the x direction. Let's make this the change in, let's just call it Vx. There we go. And then we'll have velocity x direction. Distance moved in the x direction and the x position, otherwise known as just x. Okay, so all I've done now is changed the notation, the labels. Now what we'll do, we'll take all these columns. We're going to take these, we're going to copy them. We're going to paste them in here. Awesome. Okay, let's move this graph aside. We will deal with that in a moment. Okay, so here we're going to have the force in the y direction. We're going to have the acceleration in the y direction. We're going to have the change in Vy. Again, all I'm doing right now is changing the labels. We'll get into how this actually works in just a second. Distance moved in the y direction and then the y position here. Okay, cool. Now, because I copied and pasted these over, you notice it moved over all of the formulas. So this thing goes over to N2 now. This thing is looking at the force, so that's the force divided by the mass here. The thing I need to change, though, is the time, because it's trying to look over here for the time. So everywhere I have time, I need to change this back to a B. There we go. Velocity is okay there. Change in distance, these need to become B's, just so that we're always referencing time over there, and then this is fine over there. Okay, awesome. Let's see, let's do a quick little fill handle to adjust those all the way down. There we go. And now what you notice, so these are the 2 columns that we're really interested in, is x and y, right? And let's give those a little bit of a highlight that is hopefully not too garish on your screen there. So y and x, that's the thing that we see, right? I don't see forces, I don't see accelerations or velocities, I see position in the real world. Let's suppose these are both experiencing a spring force, right? So there's a spring force in the x direction and a spring force in the y direction. And let's suppose they start out behaving a little bit differently. Let's suppose the y starts out at 0 velocity and let's say 5 in distance. And let's suppose x starts out at 5 meters per second velocity, and let's suppose it starts out at 0. Okay, they're both still oscillating, right? So this, I can scroll down and look at these. I can see that this is still going up and then down and then up and then down. Same thing with the y, it's going up and down and up and down. The question would be, what do they look like together? Now I could graph both x and y versus time. I can do something a little more clever than that, actually. Let's change this thing. Let's see, so let's change the data on here. Instead of graphing x versus time and y versus time, let's graph both x, let's graph y versus x to get our trajectory. So we're going to change the x-axis to be, let's see, let's change this to be the actual x values. There we go. And then for our series, for our y values here, we're going to make this the n column. So we'll have n and n. There we go. And so now what I'm looking at is no longer the position versus time. I'm looking at y versus x. So let's change those labels just so we don't lose track of what it is we are looking at. So this is going to be y in units of meters. And then I need to change horizontal to x in units of meters. So I'm eliminating time entirely because this is the trajectory that it's going to make in space, right? This is the trajectory that I'm going to see. So in other words, if I have a spring way down here and I attach it to a ball over here, and I start it with this amount stretched in the y and this much velocity in the x, this is the shape that it's going to make. It's going to make me a nice, clean circle. Well, it's an ellipse, right? Because it's not the same length in both directions, but it's going to make this nice little loop. It's going to keep going around and around and around because I've made that force identical in both directions. Let's suppose I change that though. Let's make the force not the same in both directions. Instead, let's suppose I make the spring twice as strong in the Y direction as it is in the X direction. So I'll double click this to use the fill handle. You notice like it's something drastically different. This is no longer a loop. This is something we call a Lissajous curve, because it's going to keep going around like this because the X and the Y are both oscillating, but they're oscillating with different frequencies now because I've changed the strength of the spring in those different directions. It doesn't quite close around on itself like that, so let's get this thing out to farther into the future. So there we get a little bit more of the Lissajous curve. You notice it's kind of forming this crisscross pattern that keeps going back and forth. It's still not done, right? It's still going over here. It hasn't looped back around to itself yet. But yeah, you can play around with that. One of the things you can do, for example, you can change this factor here. So let's change that from a 2 to a 3. We'll do a little fill handle down this way. Click, click. And I get a little bit different structure here, right? So the pattern changes, moving differently in space. And again, this is the pattern that it traces out in space. So this is Y versus X. So each one of these represents a snapshot of where the ball on the spring will be. So yeah, so there's a lot you can play around with this. You can set one of these to a constant and one of these forces to 0 and get projectile motion. So let's make this a -1 and we'll fill handle that down. And we'll make this one a 0 and fill handle that down. Okay, so we end up with this projectile motion here. Let's actually give it a little bit of velocity in the Y direction. Give it a little bit more velocity in the Y direction. All right, let's give it a lot more velocity in the Y direction. Okay, a little bit less, 50. There we go. So I end up with projectile motion. I'm back to parabolas. So yeah, so you can make this thing do anything, right? So you can now have any kind of forces working in 2 dimensions. And it's all accessible to you as a first year physics student. You don't have to know the calculus. You don't have to know all the ins and outs and everything. You just change the force in there and it will give you the trajectory that the thing will follow. So anyway, I hope this has been a helpful series to you. I hope this spreadsheet computing stuff is useful to you in your study of physics, but even more than that, I hope this gets you interested in coding. This is literally what we do all day as programmers or computational physicists. If you're interested in more, if you want to see how we do it with an actual programming language, you can check out the link in the description below. Thank you so much for watching. I will see you next time. Bye-bye.